Welcome to lecture 4 on module 2 of computer organization, in which we will be discussing about the stacks and queues along with certain examples. In this slide we will look into the stacks. We know that the computer program consists of a large number of small tasks called as subtask. It is a collection of programs or instructions that perform a particular task. So it is very important to share the information between the main program and the subroutines or the subprogram. So this is organized by a data structure called the stack. So there will be one data structure that holds the information related to accessing the data between the main memory as well as the subroutine. And these subroutines are usually, or the stacks are usually referred to as the push down stack. That means you will have for example, in particular memory location we assume that there is a stack. Push down stack indicates that when you store a particular data, when you want to store a particular data into a memory, then the first data, suppose let us assume that the data 1 is pushed to this location, data 1. Now the word push down means when you push the next data, or when you want to store the data 2 in memory or the stack, what we call, then this data 1 or the data 2 comes above the data 2, or it comes below the data 2. It depends on the type of stack. In case of push down stack, it is the data 2 comes above the data 1, and it is also referred to as the first in first out. This kind of stacks are also called as first in first out. First in first out. That means the data that is stored, sorry, this is last in first out. So this is last in, sorry, it is not the first in first out, instead it is last in first out. Last in first out. So it is like suppose you have in malls you might have seen the carrier trays that are kept one above the other. So what happens, you will always remove the tray that is present at the top of the set, and the new baskets are also placed on the top itself. So the last what you have placed will be removed first. That's what uh, the last in first out mean. The same way the data will be, the new data will be stored at the latest, will be retrieved first. So here the terms, we usually use the term push and pop. Push indicates that loading or storing the data into stack. Storing the data into stack means push, whereas pop means retrieving the data or removing the data back from the stack. Retrieving the data from stack means pop. So we usually use the term push and pop when we speak about the stacks. So here always the last data item placed on the stack is first one removed. So that's what we had discussed, that is last in first out. So in this type of stack, or in the last in first out stack, the first location will be at the bottom, and the stack grows towards the lower order address. For example, this is if the stack is pointing, the first location of the stack is pointing to the location 200. Let me assume 200. Then the first data will be stored in the address 200, and the next data, for example the address 199, the second data, second, third, and so on. That means the stack will grow in the lower order address. In this lower order address, the stack will grow. The figure in this stack, in this slide, shows the stack. So the stack ranges from, the address of the stack ranges from the bottom, from bottom, and it goes on up to particular range. So there is a range of stack. The stack cannot grow through the entire memory. So there is a limitation. There is a size of stack. So in this particular example, or in the figure, you have the bottom in which the data 43 is saved. So from there it keeps on growing, and at the last position the minus 28 is stored. So if you see, there is something called the stack pointer register. Let us know what it is. So the stack pointer, now whenever you carry out a push operation, let me assume you are carrying out a push operation. How exactly it works? Now when you perform the push operation, you are moving certain data to a particular memory location. What is that particular memory location you are intending to move? So in order to analyze, or in order to understand to which location you are going to transfer the data, the information is stored in one register called the stack pointer, SP. It is also written as SP, or stack pointer. This stack pointer holds the address of the stack. So it is not constant, it will never be constant. So when you push the data, for example, there are two possible ways. Either you may push the data of word length 32, you can push of word length 16, or of byte. So based on the word length, the stack pointer will hold the different types of address. For example, if it is a word length, let me assume this bottom address as 0x200. So this is the we can imagine this as the default stack pointer value. That means if you have not performed any push operation, or before performing the push operation, the stack pointer will have the address 0x200. Now when you perform the push operation, for example, let me take push some register R0, push R0. This is the usual syntax what we follow. When you perform this operation, the content that is present in R0, in the register R0, will move to the address pointed by the stack pointer. So what is the address pointed by stack pointer? That is 0x200. Now 0x200 is nothing but the bottom. So this will be loaded with the content of R0, the content of R0. Similarly, when you perform the push operation for the second time, push R1, or you can use push R0 again. Let me assume push R0. So when you perform the second instruction, based on the word length of the processor. For example, if it is 32 bit, the stack pointer will decrement by 4 because it requires 4 byte locations to store the data. So at that moment, the stack pointer, once you perform the push operation, the stack pointer value will gets updated with 0x. I'll write it as 196. Um, Let me not consider x because it is hexadecimal. Let me, for understanding purpose, the first address is 200, the next address becomes 196. So at somewhere at the 196 location, the data that is present in R1 gets stored. Similarly, when you perform this next push operation, the stack pointer value will be decremented by 4 again, that is 192, and somewhere in 192 address, the data R0, the content of R0 will be stored, and this process continues. This is the importance of stack pointer. Stack pointer keeps on updating, and when you, for example, after this push operation, if you are using the pop R6, now the content that is present in the address pointed by stack pointer, for example 192. Now the topmost the stack pointer is holding the address 192. Now the value that is present in 192, address 192, is retrieved back to R6 register because I have used the register R6 to pop. I can use any register irrespective of what I have pushed. For example, if I have used the instruction push R0, I need not use pop R0, pop R0. I can use any register. The only difference is the data that is present in the particular address pointed by stack pointer will be retrieved back in one of the registers, whatever you have named next to the mnemonic. If we assume byte addressable, as I specified in the previous slide, if we assume a 32-bit word length to be pushed, now how exactly it what is the process flow? Now initially you need to subtract the stack pointer address by 4. That means, as I said earlier, 0x, I'll not take hexadecimal number, instead I'll take a decimal number, 200. uh, if we assume the stack pointer value to be 200 before performing the first initial push operation, the first thing is the stack pointer value has to be decremented by 4. The stack pointer value has to be decremented by 4. So the stack pointer value becomes 196. Next, move the new item to SP, or the address pointed by SP. Now, as I mentioned earlier, you will have SP here, that is the address is 200. Next, you need to subtract this 200 by 4, it becomes 196. Now when you perform the push operation, for example move new item to the address pointed by SP, that means the new item, the value will come and get stored here. This is how the push operation is performed. So these two instructions move the word from location new item onto the top of stack, decrementing the stack by 4. Similarly, if you perform the next push, if you perform the same task again, the 196 becomes 192, and again the new item 2, and this keeps on growing. Similarly, if you want to perform the pop operation, that is here what you need to do is, initially see this particular stack grows in the lower order address. It starts from the highest address and it keeps on decrementing until the starting address of the stack, starting address of the stack. Starting address of the stack, or there is a range, as I said earlier, until the last address is reached. So here, when you retrieve, the stack pointer will be pointing to the current address. So that is the current address in this case is again 192. So you need to retrieve the data back. The new item is stored back in one particular register, that is item. So the new item, the data that you pushed in the name of new item is retrieved back in the name of item in the program. After doing that, you need to this space is empty. This space becomes, this memory location becomes empty. So what you need to do, you need to reduce the address by 4. So you need to update the stack pointer. How to update it? You need to, since it is the address grows in the lower order address, you need to add 4 to the stack pointer. So the stack pointer value becomes 192 plus 4, it points to the next location. Even then, if you want to use the pop, then if you use the same set of instruction again, the new item that is stored in the address 196 will be retrieved back into the item. We can name it as item 2, and you need to reduce the stack pointer by 2, thereby updating the stack pointer value to be 200. Now this process continues. You can push any number of data, provided you are within the range of stack, within the range of stack, and you can also pop any number of data. But the only restriction is the last data that you have pushed in has to be popped out first. That's what the name last in first out, or also called as push down stack. I hope you are clear with this. In this slide, we will discuss about some of the limitations of the stack. So here, when a stack is used in a program, it usually allocated a fixed amount of space in the memory, as we have discussed earlier. That is, it will have one starting address. Let me take it as 2000, and let me take the ending address as 1500. In the entire memory location, in the entire memory that is present in the system, out of the entire memory that is present in the system, the address that is ranging from 1500 to 2000 will be allocated for the stack. So you cannot push or pop any data that is beyond the range of 1500 to 2000. We are considering that the bottom is 2000 and the top of the stack as 1500. We are assuming. So anything that has to be pushed or popped beyond this range is not possible. That will throw you an error. So we must always avoid, that's what, we must avoid pushing an item onto the stack when the stack has reached its maximum size. That is, for example, the stack pointer is pointing now, we have started from 2000, the stack pointer value with the stack pointer to be 2000. We kept on pushing the data. We know that it will be decremented by 4 if the word length is 32-bit. So this keeps on growing, and at one stage the stack pointer value becomes 1500. At this stage you cannot perform the push operation. You are not supposed to perform the push operation, because so the stack pointer is pointing to 1500. What is the process that has to be carried out when you perform the push operation? You need to reduce the stack pointer by 4. When you reduce the stack pointer by 4, 1500 minus 4, 1496, this particular address is outside the stack, so you cannot perform the push operation. Or even though you store the data here, even though you forcefully store the or push the data to this particular memory location, you are not able to retrieve it. The entire process of stack gets corrupted, or all the data that are already stored in the stack gets corrupted. Also, it is recommended to avoid popping an item from an empty stack, which could result from the programming error. So for example, the stack pointer is pointing to 1996. Let me assume the stack pointer is pointing to 1996. You have popped the data. You have popped the data. The data that is present in this particular location will be stored in some particular register, and during the pop we know that it will always retrieve the data, then add the stack pointer by 4. So 1996 plus 4, 1996 plus 4, the address, the stack pointer value becomes 2000. So if you further pop the data, it will pop the data from the empty, so which gives rise to the programming error. In order to avoid this, or to prevent either pushing an item on the full stack or popping an item of the empty stack, instead of using the single instruction, that is push and pop, we can follow a particular sequence of instructions. So for example, in order to avoid pushing an item onto the full stack, what you can do is you can compare the stack pointer with 2000. Once the stack pointer becomes 2000, you are not supposed to push the data. Here, as and when you compare the stack pointer with 2000, if there is a conditional code that rises saying that the stack pointer value is almost equal to 2000, then you can generate an error, or you can jump to a subroutine which pops the message saying that there is an empty error. That can be done to avoid pushing the item onto the full stack. Similarly, you can avoid popping the data from the empty stack. You need to compare the stack pointer value with 1500 instead of 2000. Since 1500 is the last address of the stack pointer, so as soon as this value is reached in the stack pointer, it indicates that all the stack locations are filled. So this has to throw you the error saying that the stack is full. Whereas if you compare it with 2000, 2000 is the bottom. 2000 is the bottom. If the stack pointer equates to 2000, that indicates that the stack is empty. So in this case, when you compare stack pointer with 2000, you need to generate an error message saying that the stack is empty. Whereas when you compare 1500, if both stack pointer and the value matches with 1500, then it has to throw you an error saying that the stack is full. This is how you can avoid the problems, or you can solve the limitations that are faced in case of stack. Similar to the stack, we have one more data structure called as queue, also called as first in first out. So the stack, the difference between the stack and queue is this: first in first out is queue, whereas last in first out is stack. Last in first out is stack. So the problem in case of queue is that it starts at one address and keeps on growing. The new data are added at the back, that is higher address, and retrieved from the lower address. What happens is uh, the queue will never have a fixed address. It consumes, it keeps on growing, or it keeps on, the entire set keeps on moving from one address range to the other address range. So the two pointers are needed. In order to keep the track of the queue, we need two pointers. We cannot have a single pointer as in case of the stack, where the stack pointer alone can manage the entire range of stacks. Here in case of queue, you need to have the address, you need to have the pointers at the bottom of the queue as well as top of the queue, because this bottom as well as top is not fixed. So what happens is, in case of queue, for example, this is the starting address, or the queue starts, let us assume the queue starts here and ends somewhere here. After a few moments, the queue may be, the starting or the bottom of the queue may be somewhere here in this location, and the end may be somewhere here. So it keeps on growing from the higher address to low address. So it keeps on growing, or the entire batch keeps on shifting. So one way to limit the queue to a fixed region is using the circular buffer. That is, after reaching one particular point, for example, see here, let me assume the queue starts at 100 and we need to limit it at 200. Once the new data is added at the higher address, for example, the one data is stored in 100, the next data gets stored here, the next data gets stored here, and it keeps on. And when the last data is stored in the 200 address, the next data will be again stored in 100. Next data will be stored in 100, and this type of arrangement limits the queue to a fixed region, and it is called as the, such kind of queues are called as the circular buffer.